Thanks. So you know me already, right? So I'm going to talk about privacy-preserving AI and the foundations of indifferential privacy and privacy-preserving AI and NLP. And I'm already sorry for the very blue background, but these are sort of our official colors at Imperial. The projector is actually doing a good job toning it down so it doesn't look as ugly as it is on my screen. Anyway, so we're gonna, you're gonna see a lot of that blue. That's sort of the official color. Anyways, we're gonna look at privacy and why privacy is important or why privacy might not be important. We're going to look at the landscape of privacy-enhancing techniques. We're going to look at sort of early attempts at how to achieve privacy. We're going to have a look at membership inference attacks as sort of the fundamental adversary to privacy. We're going to look at differential privacy as a way sort of to preventing these kind of attacks fundamentally. And finally, we're going to look at their applications in AI and more specifically in NLP, which is my research focus, as well as text data synthesis. Right, so let me start you off with an anecdote that might or might not have happened to me or my colleague, as I was talked to by a colleague or collaborator, and he might or might have not, or he, she might or might have not said something like this. Hey, we need to work with this and that company and institution because they have this kind of device or mechanism that can produce this kind of unique data of a certain type. And in the country where this said company or institution is based, they don't have strong laws / governance for privacy. Right? So this example can provoke sort of different responses depending on where you give that, right? From sort of the pale sort of reactions of disgust to, okay, so what, right? And it's fair, right? Because so the right to privacy is, without getting too philosophical, is derived from sort of accepted norms and values. And these might differ based on your different societal contexts and sort of, you know, which might be different from based on where you live, where you come from, where you work. For example, one might favor the good of the community over the freedom of the individual, or might weigh it sort of differently depending on where you live, right? So even in Europe, which is very much privacy sort of centric, depending on which country you go, you might get a very different response about the suggestion of installing CCTV cameras to prevent crime. So some countries are very much in favor and they're doing that, others are very much against it. Either way, so even if privacy is sort of a core value, in practice it might become often very much neglected. And that's because it's not a goal that is sort of explicitly optimized for. So different actors, as they sort of do research, data-driven stuff, build AI models, for example, they might optimize for different goals. So the industry has a fiduciary duty to their shareholders. They need to make money, right, so that their shareholders get what they invested in. If privacy is not part of that process, then it's not part of that process, right? Academia, well, you know, if you want to publish or you want to advance your career, you might have institutional goals of extension, chasing the rankings, right? Again, privacy is not explicitly written in those goals. So, however, privacy might become important when we start looking at different use cases, right? And one use case is liability. Of course, once this is required by law, then your optimization from the previous example becomes a little bit more constrained, right? So if you're working industry, then your fiduciary duty to shareholders must be upheld subject to the prevailing regulations. Otherwise, you're losing money, right? So if you lose money, you're losing the shareholders' money rather than making the shareholders' money. So you need to make sure that you abide by the law, right? And if privacy is sort of encoded in the law, then that's your subject. Similar in academia, you might focus on still your career and institutional goals, but of course you still need to pay respect to the regulations, because otherwise you might get fired, you might get reputational damage, you might have to pay damages and so on. So examples for where these laws are sort of required and create a liability for you if you're not following them are, for example, the HIPAA in the US, which is a law that protects the personal information in health context specifically, or more widely GDPR in the EU or in the UK, which concerns the data of EU citizens. Even if you're processing the data somewhere else and you yourself sit outside of the EU, if you process EU citizens' data, then you sort of have to abide by the law. okay, well, laws and everything, maybe you live in a country where these laws are not as explicit, but at the same time, another use case, which is very much sort of law independent, is trade secrets and intellectual properties. Why do you want to protect sort of the privacy of your operations? Is because you might gain a competitive advantage. So consider that your company has spent around $1 million on either collecting or buying under a restrictive no-share license, signing a contract, a rich and diverse data set used to train a state-of-the-art model and offer its prediction as a paid-for API service. Great, right? You train the model, you can make money out of that. Well, now you have a startup X that has sampled your API, has recreated your data set for a fraction of the price, and is now offering the same service for much cheaper. In case this sounds familiar, this is a purely made-up example, but you might have heard something similar, right? And in case you're in alternative 2, not only have you lost sort of your competitive advantage, you might also be potentially liable for contract breach because your contract, sort of the data was given to you under a no-share license, right? But now, obviously, you inadvertently share the data, so someone, the original sort of data holder might sue you for that. So, and another use case, which is a more institutional perspective on why we would want to sort of share data or make data available, is, well, consider you're some big institution and you see all these sort of LLM Foundations talks that we had today, right? And you get excited, great. AI advancements are driven by web-scale data and resources that drive sort of all this improvements, right? And there's standardized public benchmarks. We have this strong performance, generalization, and general domain language tasks. Great, let's do it for our institution as well. So you want to benefit from such advancements, but then you realize that for your domain, such data isn't publicly available at scale because it's like operational data, let's say, from whatever, a law firm, from a hospital, not much data publicly available, right? So therefore, the AI performance that you're trying to sort of use degrades on these tasks because they're just not represented in the data. And then your staff says, I don't want to use AI, it only produces bad outputs, right? So what do you do, right? So do you then go ahead and take all your data and give it to the AI practitioners to train their models on it, to incorporate it in the public resources? Because you're domain experts, after all, they could benefit from this kind of AI models that are specifically trained on the data for your tasks, right? But that would then require to make this data widely available, which, if you're a hospital, if you're a law firm, if you're a financial institution, you have very strict regulations where you are not allowed to do exactly that, right? So how do you share the data then in a more private way where you respect the regulations, but at the same time you make sure that sort of whatever AI publicly available trends are going on are also incorporating your specific domain tasks. And for those who say, well, Viktor, you made up a nice story, it is actually the story that is going to happen. So there is a law coming in 2020, or has been sort of agreed upon late 2025 in Europe, which says that this law will empower individuals to access, control, and share their recurrent health data. So you need to make sure that your health data is available to the individuals to whom it belongs, but more importantly, second, you need to make sure that it's both secure and trustworthy, accessible to research, innovation, policymaking, and regulatory activities. So that means that at some point, university somewhere in France might say, hey, I want to have access to all of French people's health record under this law. So then somehow I need to be able to provide this access, right? And at the same time do it secure and trustworthy. So it is a very real problem that is going to happen relatively soon, right? So looking at the landscape of privacy preserving or privacy enhancing techniques, I'd like to do a sort of separation into two tranches. One is what I like to coin as operational privacy, or privacy is the protection of sort of data and the privacy of the data at its point of use. And these are things that you all use nowadays every time you go to an HTTPS browser, right? So these are things like encryption, these are things like being able to authenticate yourself, so making sure that the data that is supposed to go towards sort of you is only for you. You make sure that the data is not been tampered with, so that's integrity, right? People who are not allowed to access some kind of data or some kind of services cannot do that. There's also hardware sort of modules that give this guarantees at the hardware level. There are trusted execution environments to make sure that whatever code you run is not being tampered with. And all this is essentially a bunch of applications that are built on cryptography as a foundation. So both encryption, confidentiality, authentication, trusted research environments, hardware security, these are all built on cryptography. And cryptography is a formal sort of framework which provides you with very strong guarantees about the unlikability of being able to tamper or to essentially crack these encryption primitives, right? Now, if we look at another sort of strand of privacy, is what I like to call release privacy, and that is when we are looking at how we can protect the privacy of the data after some information about that data was released intentionally, right? Like, for example, publishing statistics, right? And here we look more into sort of different types of approaches. We look at data substitution. For example, if you share a document with sensitive names, there was a US sort of story where they released a lot of data with a lot of redactions, right? So you might have heard about this in the news. So you redact whatever faces, names, and so on. So that's data substitution. You might do this kind of data substitution not based on the data, but rather based on the way how the data looks. So this would be then called syntactic anonymization. We're going to look at an example of how that looks like, which is typically makes sense for sort of structured data, right? There are disclosure risk assessments, which is a method that has been around for a while, where you sort of release the data and then you have a look at what happens, like how likely is it that we disclose any information that was not intended to be disclosed, and then you adjust the release until your likelihood is relatively low that you can stomach it. And finally, we're going to look at differential privacy, which is a sort of similar to the left-hand side formal sort of framework. Differential privacy is a formal framework for the release privacy of data. So every time you have something about the data, you release some information about it. If you do that in a differentially private way, you can obtain some guarantees about essentially the disclosure risk, right? So now how does all this have to do with AI? And the argument is that privacy in AI requires both, right? So let's say you have trained a machine learning model, great, it performs well, but unlike a traditional software system, you cannot enforce the same level of fine-grained access control. So, for example, in a database, you might have different roles, right, where you have an admin that might access everything, and you might have a user that has access to only a certain set of tables, and you have another user that has only access to a different set of tables. Now, if you train an AI model on all of these tables, you cannot enforce the same level of control, right? At least not yet. And if someone else has an idea, then maybe if they publish a paper, they become very famous for it. So therefore, like for now, at least, we are going to treat anything that ingests the data and then produces outputs, such as a machine learning model, right, based on based on these inputs, right, as a form of data release. So this will then go into the release privacy. Of course, we need to look at operational privacy as well, right? We will need to make sure that people who are not allowed to access the model at all are still not allowed to do so. But the release sort of privacy is the thing which gets more interesting, where we essentially protect the data that our AI algorithms are ingesting against sort of unwanted meddling with in terms of stealing that data or breaching the privacy of that data. Now, okay, great. So why don't we just do the famous US example of redacting everything with big black bars, right? Well, so first of all, you have to do that manually, and if you have whatever 22 billion tokens of pre-training corpus, right, you're going to do that very long. So then you go and see, okay, how can we do that automatically? Well, automatically you need to maybe train a tool that does so, like an entity recognition or some kind of sort of heuristics, right? But the point is it doesn't guarantee you 100% recall, so you will always miss something. And even if you know what exact strings you need to match, right, even if in your training corpus there's a typo, you still miss that, right? But even if it did, anonymized data, and even if after it's been aggregated, can be re-identified. And if you don't believe me now, I'll show you a couple of examples later, hopefully to convince you otherwise, right? So Also, outside of the US, with the HIPAA law, there's no real clear definition and no regulatory consensus on what is actually de-identified enough, right? Because as we also will see, some information by itself might not be identifiable, but then if you link it with some other information which by itself is also not identifiable, it then all of a sudden uniquely identifies you in the crowd of millions of records. So let's have an example of how a supposedly de-identified examples looks like. That's from a mimic data set, which is essentially a dump of a hospital database from the US, which also contains free text summaries. So we can see here, it is de-identified. We have doctor known first name, known last name, is a retired, and so on, presented to some other doctor name pattern, and doctor, and so on, So all the sort of blatantly obvious identifiable attributes have been removed. So good? Well, not really, right? Because let's have a look at what we can infer. So we know that the good doctor is a male. So that already sort of removes 50%-ish of the population. We know they were 71 between 2001 and 2012, which is when the data set was sampled, right? So that again removes a good chunk of the population. We know that they must live around Boston because that's where the data set is coming from. And we also know that they're a retired orthopedic surgeon, right? So how many 71-year-old Boston retired orthopedic surgeons are there? Probably not that many, right? And this is only from the first two sentences from this example. We then go ahead and look on social media. Maybe they have a social media account, right? Maybe there was some news article. So we get some publicly available information. And this is a good example of how these things by itself, all these informations may be not identifiable or do not make an individual identifiable. If you then start aggregating this information, they very well might, right? So, and that's why we have to stop there, because the Mimic 3 data usage agreement, in the first point, it says I will not attempt to identify any individual or institution referenced in this data set. So that's basically privacy by goodwill, right? I swear I won't do that. Okay, fine, you won't do that, right? So that's basically an agreement that if you have to honor. And there are some examples of real re-identification. So it has been argued that 87% of American can be identified by zip code, birth date, and gender alone. And that's sort of what started this whole, or it was one of the triggers for this whole research direction. This led to the identification of a US governor's medical information from an insurance data set, though it also was a bit lucky, right? More recently, Catholic priests identified from aggregate usage statistics that are being sold by the dating app Grindr, one of their own, right? And then they started harassing them. So that's basically an example of where, this identification actually leads to some real world human harm, right? Maybe you don't want to be identified from the usage of sort of statistics of a dating app, right? So this led to the notion of k-anonymity, which is a first approach to try to combat this kind of re-identification that was proposed in 2006. And the notion was focused on preventing identifications, similar like in the example that we did before, mostly on structured data sets, in fact. So the goal is to make each record indistinguishable from at least k-1 other records with regards to a set of quasi-identifiers. So if you want to enforce 2 anonymity, right, you need to make sure that at least, or 3 anonymity, no, yeah, exactly. If you want to make sure that you're 2 anonymous, your data set is 2 anonymous, you need to make sure that each data point is indistinguishable to at least another data point with regards to a set of quasi-identifiers. Now, quasi-identifiers is something, basically column names that you can decide which ones you want to focus on, and these are typically attributes that are assumed to enable re-identification, such as in this example, zip code, birth date, and gender, right? So the way this is achieved is by performing data modifications, most prominently generalization, where we have a sort of specific value and we can generalize it up to remove some of the specificity by generalization. Attributes like names we need to remove entirely, right? It doesn't make a lot of sense to generalize a name. Binning, that is essentially the generalization equivalent of numbers, where we, instead of reporting an exact number, we bin it into a sort of bin of plus minus values. Microaggregation does the same thing and then changes, instead of having the bin, it just has a representative value for that bin. And then there's also sort of swapping and perturbation as other approaches which sort of play around with your data to make it look a little bit different than the original one. So to present an example, we have this data set of Alice, Bob, Carol, David, Eve, and Fiona, which have an age, a postcode, these are UK postcodes, sex, and a condition, right? And this data set is obviously not k-anonymous with respect to the quasi-identifiers age, postcode, and sex, because the postcode alone is already uniquely identifiable, right? So in order to achieve k-anonymity, and in this case 2 anonymity, we need to perform the following data transformations. So we bin the age here, we generalize the postcode, and we remove the name. Obviously, names are also uniquely identifiable, right? So this leads us to this example here. We have generalized the age, we have generalized the postcode, and we have suppressed the name. Now, for each example, with respect to age, postcode, and sex, there's at least another example which has exactly the same set of attributes. Right, so here, row 1 and row 3, row 2 and row 4, and row 5 and row 6 are indistinguishable with respect to age, postcode, and sex. So if you say, I know something about this person, it might as well be this person. So you can't really identify which person you're referring to based only on the set of quasi-identifiers, right? Okay, now this sounds good, but in practice, maybe the more observant of you have already identified the problem here, but if not, I'll show you immediately, right? So the limitations of this approach is, for example, this is not very robust towards the so-called homogeneity attack, which is if we have k records in a group that are all k-anonymous, such as, for example, here row, was it 2 and 4, no, 1 and 3, right? Row 1 and 3, they are k-anonymous because there's 2 of the rows which have the same quasi-identifiers, but it doesn't actually matter because if we wanted to learn about the condition of any of those persons, it's the same condition, right? So it doesn't matter that we can't tell whether Alice is row 1 or row 3. If we want to learn that Alice has diabetes, we have done so now because both row 1 and row 3 have as condition diabetes. So we're not really protecting, we're only protecting identification, but we don't really protect anything about inference, right? Okay, so there's, again, a way to kind of deal with that, and it's supposed to be L diversity. I'm not sure if you can read that. It's a bit too gray maybe for this beamer. So the idea of L diversity is to make sure that each equivalence class must have at least L distinct values for sensitive attribute, like as condition here. So we need to, in order to achieve that, we need to generalize further, right? We need to merge essentially rows 1, 3, 4, and 5, 1, 3, 5, and 6. Sorry, yeah, 1, 3, 5, and 6 in the same H bin, essentially, and then we need to get rid of the postcode as well, because we can't generalize SW7 or E1. We need to make postcode basically UK, right? But then this achieves exactly what we want to achieve, even if we sort of can identify anyone from this cluster. We cannot with certainty say what is the condition that you can infer, which we can do here. Again, there's another attack, which if you have this external information, which I hinted at before, if you sort of link something either based on prevalence and statistics or based on whatever social media news articles, you might infer still or reason about probabilities about how likely someone is something, right? So for example, a very Singaporean example, I live in Singapore. If you know that someone is Malay and you see that they have diabetes 2 in their equivalence class, you can reason about the likelihood of this person being Malay, because the prevalence of diabetes in Singapore among the Malay subpopulation is higher than among other subpopulations, and I think roughly twice the sort of relative amount. So the point here being is that all these are, we can go ahead and try to fix that as well, but then there's another attack that we haven't thought of. These are all kind of post hoc modifications against specific attacks and not a fundamental and guaranteed protection. So, and a sort of more generic attack that does not, stop in front of any of these data modifications is the so-called membership inference attack. And I will give you a somewhat silly example, but is a very sort of visible example, right? So where we can show that even if you look at aggregates, you can guess about whether someone has contributed to the output of the aggregate or not. So let's say we have a billionaire. You can make up your favorite name, right? It's very secretive, and he has moved somewhere to close to a town where you live. And depending on whether you love or hate billionaires, right, you might want to figure out whether or not they're living in your sleepy town of only 5,000 inhabitants. Well, now your town is modern, and they report digitally the mean income per household per year. So you can go ahead and then query this register to see what is sort of the average or the mean income per household in your town. And then you might get the answer something like 40K USD or whatever sort of the average annual income per household in your area is. Or you might get something closer to like 6-fold or 10-fold of that, right? And then either way, you have a good guess whether or not this billionaire has moved into your town or not. And that is, of course, because a billion as a annual or whatever annual salary net worth, right, is a outlier compared to the average sort of income of any other person, right? But this is also a very simple query. Just query a mean of a number, right? It wouldn't work the same with age because age is normally distributed, whereas here we have a clear outlier outside of that normal distribution, right? So no one can live to 1 billion years old, but they can save up to $1 billion dollars of money. Right now, if we look at sort of more rich data, of course, again, due to the coercive dimensionality, we have more dimensions. So therefore, we can have more outliers, right? So maybe income or age alone is not a identifying feature, but then if you combine it with a bunch of other features, then all of a sudden everyone is an outlier, right? And then you can perform this kind of queries in order to mine the membership of a specific data point or a specific individual representing the data point, or that is representing by the data point, to the overall output, right? And then you might do something evil to that billionaire, right? So to give a more formal definition, given a datum here and an output of a mechanism, f of x, so the datum would be the billionaire for which you happen to know their whatever net worth or mean income, right? And the mechanism would be the query, querying the register, sort of producing the average output, right? Of the dataset X, which is sort of all your town members here. Your goal is to determine whether he is element of the dataset X or not. So in other words, in very plain English, the question is, was a specific individual's data used to produce this output? There are a couple more examples, of course. So did sort of looking at convict rehabilitation statistics, was my neighbor included? Looking at this research paper's results, was this guy over there an individual and the participant, right? Was the AI model that was trained here, was it trained on my data or was it not trained on my data? And why this matters is twofold. So one is, again, going back to whether or not you want to reveal some sensitive information, such as, for example, whether you were a convict, might be not something that you are particularly interested in, right? Again, depending on where you come from and how your sort of values are aligned. But from a research perspective, the membership inference attack and sort of this whole membership inference mechanism is the most basic privacy attack that you can mount, right? Because if you can successfully defend against membership inference, you can't infer anything else, and that is because you have a so-called plausible deniability, right? So if you can say, oh, I learned something about you from this data, if there's a plausible deniability that you can't even prove that I was part of this data, then everything that you sort of built on top of that doesn't follow, right? And this also gives us a formal notion of privacy. So the strongest requirement that you can have is that you can't even tell whether someone has contributed to the output, whether they were part of the initial data set that was used to calculate this output, for example, the average or train an AI model. Okay, so how do we evaluate the accuracy or sort of the performance of such a membership inference attack? Again, the question is, was a specific individual's data used to produce this output under this definition? So we usually, as we do, we create an evaluation data set where we have sort of the data format is like this. We have a datum here, right? So the data point, which we want to check whether it's member or not. The output of the mechanism that we want to look whether, sort of that we want to infer from whether the datum contributed to the output over the dataset X, which we want to check whether the datum was part of the dataset or not, right? And the evaluation matrix, of course, this is because you can either predict yes, it was, or no, it wasn't. It's basically binary classification with the corresponding metrics. We can use accuracy, true positive rate, false positive rate, and so on. And of course, if the classifier outputs a confidence score rather than a simple yes, no, you can go ahead and draw this area under the curve. Metrics, usually true positive rate at false positive rate, or sometimes also precision and recall. So, and then it would look somewhat like this, right? So on the right, you have your false positive rate, and top you have your true positive rate. The random guess goes like this, so which means that as your false positive rate rises, exactly like that rises your true positive rate, so that's basically randomly guessing, right? And if you move towards this quadrant, more closer towards this quadrant here, that means that you get more or a lower false positive rate for a higher true positive rate, right? So that means that for a false positive rate of 20%, you might get a true positive rate of 80%. That means out of the 20, like probabilistically out of the 20% of the data set, you classify 80% correct. Now, this is sort of the fundamental setup. Again, going back to AI and LLMs and your machine learning models, why should we care, right? Well, that's because depending on what kind of access to the model you have, you can mount these membership inference attacks rather effectively, right? So one of the papers showed, as an early example of why privacy might be relevant in LLM training, that you could memorize training instances directly through data generation, because as we have heard, models might overfit to their training data. They might sort of, if you prompt them with the right prefix, they might just continue and generate that. So if the prefix here is part of the training data, you can just continue and generate the rest of this training instance. For example, you could start with Viktor's credit card number is, and then if that was part of the LLM's training data, it would then go ahead and generate my credit card number, right? If you don't have, or if you have more access, so something like the training dataset distribution, you can train this membership inference attack classifier like this directly. So you can, for each data point where you want to test the membership, right, you can sample from the data distribution to create a data set where you then train a in model, which is trained on the data set with the data point, and an out model that is then trained on the data set without the point. And then you run your actual model, which you want to evaluate whether it was trained on the data point or not, get the confidence score, and then you check whether it's more closer to your in model or your out model. So based on that, you can pretty well guess whether a data point was used in classifier training, right? Or model training. If you don't have access to the data distribution, no worries, it works as well. So for example, if you assume that a data point that has been trained, or that has been seen during training has a low sort of loss because it has already been seen during training, you can go ahead and perturb that a couple of times, and then you will assume that if the loss on the original data point is much lower than those than of the perturbations, which are unlikely to have been observed during training because you just created the perturbation randomly, then it means that your data point has been observed. Whereas if there's no statistical difference, it means probably the data point has not been observed. Right, okay, we've heard that with large language models, we don't need to train them anyways. We have all this ICL and RAG, right? But bad news, you can also jailbreak in-context learning and RAG, right? So you could go ahead and sort of try and mine the system prompt or whatever the user instruction that is hidden from the API usage in order to mine the potentially private training sort of in-context examples that are used in order to improve the LLM's inference, even if it wasn't trained on these data points specifically, right? Okay, so I hope this sort of gives a good motivation as to why we should care, given all the sort of more general motivations of privacy and why we should care particularly for LLMs and AI training, right? So how do we then deal with this kind of problem, right? We want to have data, but at the same time we don't want to have we don't want to share that data publicly so that everyone can sort of access it, right? So the goal is, as we mentioned before, We don't want to represent any individual or being part of the data set. We don't want to allow to infer any information about this individual, whether or not it was part of the data set. And sort of at the most basic level is sort of the membership inference. We want to prevent membership inference. We don't even want to allow to infer if an individual was part of this private data set that you want to share or that you want to share an output on in first place. Right? But at the same time, okay, well, I think I have a very good example of how to achieve that. You just share random data, random noise, right? Random noise you can't probably infer anything from, but at the same time, of course, we want to make sure that the data that we share or the results that we share out of that data are somehow useful. So you want to preserve structure and relationships, you want to preserve like characteristics, you want to make sure that the statistical results are kind of similar to what we expect it to be if we just run it on the data directly, right? So what we want to have essentially is something that is similar if you sort of squint your eyes, but at the same point at every specific instance it's fictitious. So this looks somewhat like this. You have a private data repository here, which you then use a privacy-preserving data sharing mechanism to obtain some kind of shareable output. And this kind of privacy-preserving shareable output the sharing output guarantees that the risk to identify any single individual is quantified with respect to sort of whether or not they've contributed to the private data, but based on looking at the shareable output. Right, so how do we achieve that? And we achieve that intuitively by adding noise in order to mask out each individual's contribution. So the following example, again, a bit silly, but it gets to the point quite quickly. You ask a survey participant, have you ever cheated on taxes or cheated on your partner, right? So something that people might not want to answer truthfully, especially if their answer can be then attributed to them, right? So the way to deal with that is you flip a coin, or you ask the participant to flip a coin without showing the result, and then only if it lands on heads, they need to answer truthfully. Otherwise, if it lands on tail, they flip a coin again and essentially then give a random answer, right? So in this way, you have, at the individual level, you have plausible deniability. Have you cheated on your partner? Yes, but it was a coin flip, right? You don't know. So you have the plausible deniability of each individual, but at the same time, you can reverse engineer depending on the true set of probabilities what the actual sort of answer of a set of people answering that query would be. So if I ask here in the room, for each individual, we have plausible deniability. Overall, we get a pretty close estimate of what would have been the answer if we have done that without flipping the coin, right? So another example, and here we go more towards databases. So if you wanted to query, is the salary of person X above $N, right? So we take the adult row, sort of the target row of that adult database, which stores their name and their salary, and then we ask, okay, is the salary of that sort of row bigger N, and is that data set 0 or 1? So if the answer here is 1, then you know that the answer to this question is yes. So that might be privacy breaching, right? If you don't want to tell how much person X earns. So, but if we add noise to this calculation, with some calibrated noise, which we will discuss about how to calibrate that, we might get an answer something like 2.5 or 0.2, right? So that means we can't exactly infer whether or not this row actually exists. And this is, again, you can't tell exactly. You have the plausible deniability at the individual level, but if you run the query on the whole data set of the whole data set of this sort of database, you might again, you add enough noise to mask out an individual's contribution, but overall, the final output that you get here is relatively sort of close to the original. So I hope this intuition makes sense, because we're going to formalize it now. And this is essentially exactly the intuition behind differential privacy. And the intuitive definition is that a mechanism that takes as input any data set and produces a result. So this is what we have talked about, sort of this sharing privacy, right? Differential privacy gives a guarantee that if you look at the result, the likelihood to infer whether or not any individual raw or individual's data was part of the input of the data set that was used to produce that result, and that's fixed below a certain bound. So the mathematical formulation here looks like this. a randomized mechanism F here satisfies epsilon differential privacy if for all data sets X and X prime that differ in a single row, so between X and X prime, which are two data sets, there's only one data point of difference. And for all possible subsets S of F's output space, so this is a probabilistic mechanism, so it will output probability distributions. So for each part of the probability distribution in the output space, the ratio of the probability of observing the result with and without the datasets is bounded by sort of e to the power of epsilon. So this is very sort of mathematical, right? But we will see how it looks like if we have a visual representation of that. There's a extension of that of approximal differential privacy, which says basically exactly the same thing, but it leaves a room for error, and that is the parameter delta here. So with the probability of delta, we don't say anything, but with the probability of 1 minus delta, this is guaranteed, right? So that makes sense to keep the delta low, and for all the mechanisms that implement this, like delta is vanishingly low, and then even if delta is surpassed, then sort of the probability of having a catastrophic breach where you really guarantee nothing is goes towards impossible relatively quickly. So the difference to K anonymity here is that DP gives us guarantees at algorithm level and applies to all possible inputs and outputs of that algorithm, regardless of how the data looks like, whereas K anonymity modifies the data itself. So by definition, sort of tied to the data, right? So some examples of mechanisms and data sets and outputs would be, so a mechanism could be an SQL query, and the data set here would be the database it's run on, and the output would be a query result, like for example, a number of rows, right? Another one would be ML training, so we train an ML model on an ML data set. That's the mechanism. The data set is the ML data set. The output would be the ML model. Or another example would be data synthesis, so you have some kind of data set which you want to synthesize a sort of synthetic version of. So your mechanism would be data synthesis, and then your output would be the synthetic output of that data synthesis process. Now, I've talked a lot about probability ratios and sort of epsilons and bounds, but let's have a look at how this looks in practice. So let's have a look at an example of 26 data points in 2D. So it looks somewhat like this, right? 26 because we have 26 letters in the alphabet. And the neighboring relation between those two data sets is basically adding or removing this point y. And the mechanism that we're going to look at is the sampling from a kernel density estimate. For those who don't know what kernel density estimate is basically like the probability distribution of the data here. So the more data points you have along each dimension, the higher the probability density would go there. You can obtain that with the KDE, and then if you sample from that, you get a probabilistic output based on, basically what you sample from the KDE, right? And if I look at the KDE by itself, here is the KDE of the data set with the point y, and then the same dashed line, dashed blue line, is the KDE, so the probability distribution of that output of that mechanism without the point. And you can see that there's quite a stark difference. So if you're a crafty, reverse engineer, you could look at these two probability distributions by sampling often enough from this KDE to see that there might be a point missing here, right? And what differential privacy essentially does is it says for each point of this output, the difference between if you divide one by the other can only be so much, and specifically only so much as you set it with the epsilon parameter, right? So if you look at the right-hand side, the differential privacy bound of 0.97 gives you an upper bound of here and a lower bound of here, and we can see that obviously the ratio, so if we divide the blue line by the blue dotted line at each point in the interval, we get a big spike here because the blue line here goes much higher than the blue dotted line. So we have a spike here in the differences, and this violates the differential privacy bound. So all the differential privacy says is that for all kind of outputs here, your ratio in the probability distributions cannot go below, above this bound or below this bound. So I hope this makes sense visually, and because this is bounded, then by looking at this kind of distributions, you cannot tell whether or not any single point has contributed to this output or not. And of course, at the same time, I mean, this distribution is way more expressive, right? You have here two peaks, which represent that there's a agglomeration of points here and here. Whereas if we looked at the smooth distribution, it sort of doesn't tell you much, right? So you get the privacy, but at the same time, you lose the utility that you would have otherwise gotten from the non-privatized distributions. Right, so there are some nice properties of differential privacy, and that is one of them, and we will come back to that again, is post-processing. So if you apply something, if you apply differential privacy to a mechanism and you take it out, its output, whatever you do with the output, as long as you don't go back to the original data that it was applied on, the output is differentially private. So you can't sort of lose privacy of that output by doing something with it. We have sequential composition, and that is the more we sort of apply the same mechanism on the same set of data, the more privacy we consume, and there will be another example for that later, but we don't have that for parallel. So if we apply the same mechanism of this joint set of data, again, this does not apply, or this does not violate the privacy jointly, so sort of whatever is your maximal bound for each of the processes that you apply to a disjoint set of data, that's your maximum bound epsilon. And so why differential privacy is interesting is because it's essentially the inverse of membership inference, which is what we have shown before, right? There's some theoretical work that shows that the differential privacy bound that we have discussed before, so these ratios essentially, can be expressed as a worst case success rate of a membership inference attack following this formulation. So what that means is if we look before at the, okay, that's too far away, but anyways, if we look at the sort of area under the curve plots, here we might have a sort of curve like this. What differential privacy gives us are these upper bounds of how far to the left the plot can possibly go, right? So for example, for the yellow bound, so it's dependent on the epsilon. The lower the epsilon, the more the sort of the bound goes towards random guess, so towards the middle. For example, the yellow bound here that is given by epsilon of equals 1 basically suggests that the actual observed membership inference attack here in the yellow not dashed cannot at any point go over the maximum guaranteed sort of theoretical worst case. So this is how, or this is why differential privacy essentially prevents membership inference attacks, or at least gives them a upper bound of how successful we can perform a membership inference attack, right? So this is basically here written down again what I just said. So let's have a look at how this looks in practice, how we implement differential privacy mechanisms or algorithms. So we have, once again, a very stupid example, but I just said differential privacy works for any kind of data sets, regardless of how many data points they have. As long as the mechanism is private, it has to be private to all the data sets. So here we have a data set that is Viktor's secret service agent of maximum size 1, right? And we want to run a count query. So the possible output is 0 or 1. So we obviously don't want to reveal whether Viktor is secret service agent. So if we get output 0, we know it's not. If we get output 1, we know it is. So in order to add the noise and to calibrate how much noise we need to add to obfuscate this any single contribution, we need to know how much any single row can contribute to the final output. So here, the query that we want to privatize is count. So it means that any single row can only contribute 1 to the final output, right? So either you count it or you don't count it. If you count it, it's 1. If you don't count it, it's 0. So the difference is 1. So which means that we might get some output somewhere between 0 and 1, so 0.43, right? And based on that, we cannot actually know, is this sort of 0 plus some noise, or is it 1 plus some negative noise, right? So essentially, this is, as I mentioned, one of the mechanisms to add noise here is the Gaussian mechanism, where we sample from the normal distribution. And there's, again, if you look into the literature, there's exact calculation of how exactly you obtain this. The point is that it depends on the epsilon. So the more privacy you want to guarantee, the more noise you want to add. It depends on the delta. So the lower you want to make sure that the sort of your mechanism fails, the more noise you need to add, because it's here its logarithm of the delta being divided, and it depends on the sensitivity S. So the more your mechanism, the more for your mechanism each individual contributes to the final output, the more noise you need to add, because again, it's at the top of the fraction, right? So now if you look again a bit more closely into the composition, so why is it that if we compose the same query over and over, we lose privacy? It's because, well, we can estimate the distribution based on we know that noise is being added from a normal distribution. So if we sample enough times from that mechanism, with some unknown mean, but observed distribution around that mean, we can then estimate the noise parameters and deduce the true answer. So here, that would be, that looks different for me, but this would be the distribution centered around 0. So if you sample enough points and they start forming this distribution peak, you would know that the answer is probably somewhere closer to 0. Or if it starts instead forming a distribution with a peak like that, you would know it's probably somewhere closer to 1, right? So as a rule of thumb, each axis of the mechanism's input data contributes to the privacy bound and therefore needs to be accounted for. The very simple way of doing that is just counting all the axes and then summing them up. It's also a very inefficient way. There's multiple ways of improving this bound. Basically, what you want to achieve is you want to make sure that you add so much noise that for the amount of times you want to access the data, you cannot effectively infer a distribution or you cannot infer the mean of the distribution between, in this case, 0 or 1, right? So you need to add so much noise that basically these distributions both look very similar based on what you can infer from the data that you obtain from sampling from this mechanism. Right, now let's have a look at a different mechanism, and that would be now the sum query over the same data set. Well, again, we need to determine the sensitivity, but the problem is that unlike count, which each row only contributes 1, now we're looking at integers, and integers are potentially infinite, right? So what do? We can't add infinite noise, because if we add infinite noise, then nothing makes sense anymore. But what we can do is we can think about what are reasonable values for age. Again, and unlike income, which we had before, age does not scale to 1 billion. The oldest ever person that we have known of is 122. So we give a bit of leeway there. We clip the age to 125. So the sensitivity of our data or of our mechanism would be 125. So which means here for sensitivity, we replace 125. And then the possible output here is somewhere between 0 and 125. Plus a noise, so the actual output could be somewhere between 68, something like 68.3. Right, so now I talked a lot about how we build this, but of course, because this is a formal method, we talk about guarantees, right? So we need to prove that this guarantee holds. So unlike empirical methods that we have seen before, so even the power laws that we have discussed, they're not really laws, right? They're just observed things. Whereas this is a formal method, as you learn in maths, right? As you learn in maybe logics, formal computer science methods, you need to prove that whatever you have come up with actually holds, which is something that I've been avoiding so far because the proofs are very long and boring. I just try to get the intuition behind it over to you, right? But you need to show that whatever you have come up with satisfies these differential privacy guarantees. And that's an active research field where, again, many building blocks like this Gaussian mechanism, which adds noise that I have just showed before, exist. And then the goal becomes essentially to assemble these building blocks most of the times and show that what you have built together satisfies the privacy guarantees, right? So many of these building blocks are already implemented in quite mature libraries, such as TensorFlow Privacy, Opacus, and others that are coming out in order to perform essentially differentially private machine learning. So the way you build a differentially private algorithm, again, on a very high level, is you come up with an algorithm that you want to privatize. You identify all the points where you access potentially private data. And again, as a rule of thumb, each access of the private data requires privatization. You identify the sensitivity of each of these data accesses, like, for example, is it a count, is it a sum, or for any other functions, you need to essentially come up with sensitivity of that function. And then you compose all these accesses in order to obtain a final budget and how sort of each of the accesses relate to the final budget. And then you calibrate the noise that you need to add during each of these accesses based on the sensitivities that you have obtained in order to obtain a desired epsilon and delta that you want to guarantee for. And then you prove that what you have done is correct, right? So an example of this, and this is where we move again to machine learning territory, is differentially private machine learning. So your input is some kind of machine learning training data set, and your mechanism is model training with stochastic gradient descent, so as we have seen multiple times, and essentially backpropagation. So the outputs here that you have are parameters of some trained machine learning model, and the actual output would be then some machine learning model with the differential privacy guarantee, right? So this looks somewhat like this. This looks very similar to the stochastic gradient descent algorithm. There's a couple of things are different here. We sample, which we usually don't do, right? We just have batches, but here we sample randomly, we compute the gradient, and then we descent, right? So what we do now in order to prioritize this, let's have a look where we access the data, right? So we access the data here, so there's a random sample, and then for each of those examples in that random sample, we compute the gradient, and then we perform the descent, and then when we output the final model has the weights that has been calculated through the gradient descent. So the outputs of the model have were contributed to by this calculation, which once again had access to the original data. So these are all the steps that we need to privatize. Now, when we compute the gradient, so we are basically privatizing the gradients here, right? When we compute the gradients, we need to add noise. And because the gradient can potentially be, again, infinite, right? It can be infinitely big, infinitely small. We clip it to bound the sensitivity of this operation. So first, we clip it like with the sum. In the sum, we say, okay, in the sum example, we say it's between 0 and 125. Here, we just set an arbitrary bound. And then we add noise to hide each example's contribution. Again, how we get to that noise is a bit more complicated. That's basically the core point of the paper. I'm not going to go into detail. And then we repeat that until we run out of our budget that we have set before. So here is where we do the accounting, because so it's not as simple as just combining sort of each data access, because we have a random sample here. So if we just sort of add all the steps and add all the privacy accesses that we have had here, then as a result, we will overestimate how much sort of noise we need to add by a big amount. So therefore, in the paper, they actually come up with sort of a way of calculating this privacy budgets more tightly. Again, we're not going to go into detail here because it's like a couple of pages of proof. But the idea is like this. Essentially, in order to ensure privacy, you add noise when you calculate the gradient, and in order to bound the sensitivity of this operation, you need to clip the gradients, and then you repeat that until you run out of your set privacy budget. Again, this is something that is very mature and implemented in the libraries. You just need to set the hyperparameters of the budgets and the budgets and the repetitions that you want to maintain. Now we have trained a model with let's say the DPSGD, so we have a differentially private model, right? The probability of doing membership inference attacks against that model is bounded. So how can we evaluate that model, right? And the answer is they're twofold. One is we perform downstream evaluations. So we're looking at the utility, and the utility of a model is typically measured by its downstream task, right? So for example, if we look at the MNIST data set, which is classifying handwritten digits, we want to look at the accuracy. And usually we look at it as a function of the privacy bound, because we want to see how the utility of the model that we trained suffers with as we sort of ensure more privacy. And suffer it does, because the more privacy we ensure, the more noise we add. And here's an early example of where, for different levels of noise, we get essentially different levels of training accuracy. So here it goes from 90 to somewhere to 95 to 98, depending on whether we had a lot of noise or if we had little noise. And often we do that in comparison to a non-private model trained on the same data set just to sort of get an idea how much utility we lose compared to just training the model. At the same time, we still do the privacy evaluation, right? So we have a formal proof that shows that the idea is sound. We have proven it, but there's still plenty of room to make errors when we implement our idea, right? And because the empirical scores are obtained through the implementation, we also need to make sure that our implementation is bug-free. So we run membership inference attacks, if only to make sure that we have implemented everything correctly and there is no privacy violations according to the theoretical worst-case scenario. So these so-called DP audits can help us uncover bugs in the implementation. A little bit about audits. So in the DP threat model, we assume that an adversary, so someone who wants to mount a membership inference attack, has access to infinite computation, perfect background knowledge, and unrestricted access to all the privatized outputs. So for example, for the DP SGD example, it would be they would have access to the gradients, right? Which doesn't really make a lot of sense. You wouldn't release the gradients of your trained model. You would release the model maybe, but because this is sort of the worst case scenario, you assume that the sort of the best attacker that can come up with has access to all of these, and still they can't surpass the guarantee that you give through differential privacy. So this is helpful to conduct these so-called audits and verify that this worst case guarantee that your algorithm is supposed to guarantee is actually holding. And there's sort of some vivid work on performing exactly this. So here's a differentially private, like a widely popular differentially private data synthesis method. And there's been an audit years after this was published to show that actually none of the implementations that implement that algorithm are private by design, right? So they have also made some mistakes which violate their privacy guarantees. Still, the paper got published. They got like very good results using a buggy implementation that sort of underestimated of how much privacy they have actually they can actually guarantee. So they, but yes, so this way you can verify that whatever you have implemented, even if your proof is correct, whether your implementation is correct as well. And indeed, if you make use of all that information, again, other papers show that the theoretical bound can be reached even if the implementation is correct, right? Using sort of the worst kind of, or using the strongest possible adversary, which can, for example, craft their own data sets, right, in order to train that model. So if you have data sets that consists only of outliers, then of course, looking at the results, you can identify the outliers much more simply, like the example of the billionaire. So you can create similar examples for machine learning algorithms. Now, in reality, of course, you don't have access to infinite computation, you don't have perfect background knowledge, and you usually also don't have unrestricted access to all these outputs. So the more of these assumptions you sort of release, the more realistic your attack becomes. So if you have developed an attack that has minimal assumptions and still comes very close to the sort of theoretical privacy guarantee, then it's bad because it means that, or it's good for you because you've come up with a strong attack, but it means that, even with the minimal assumptions that are available sort of for everyone, this kind of guarantee that you guarantee can be, the worst case guarantee or the worst case sort of privacy breach can be achieved. So here, from another paper, they look at what kind of different sort of assumptions we can make, how you can access the model. Either you just have an API yes/no kind of output, or you have a black box, white box output where you have either access to the logits or even to the model weights. You would be able to look at the gradients that are supposed to be privatized, right? Or even you could craft your own data sets. And then the more assumptions you make, the stronger your attacks become. Obviously, up to the point where you can actually reliably reach the the theoretical bound that is guaranteed by differential privacy. Right, so just briefly, we mentioned composition, and due to this sort of sequential composition property of the differential privacy, each data released on the same data set affects the overall privacy budget, right? So if we run the same query against Viktor Secret Service Agent multiple times, we can get the distribution. Similarly, if we train 10 models on the private data set, they're all private, but then due to the composition, if you take all these models together, you have a bigger attack surface. So in order to still maintain the privacy guarantees, you either increase more noise to account for this repeated access, which reduces the utility, or you prevent the access once the budget is exhausted, which is kind of bad news, right? You wanted to train an 11th model, and then the data provider says, well, no, bad luck for you. You exceeded your privacy budget. So an alternative solution to that, and that's sort of going a little bit into the research direction that I'm working on, is to look at generating privatized synthetic data only once, and then perform all the follow-up, so sort of analysis and model training and so on this synthetic version. Why is this good? Is because due to the post-processing property, we can guarantee that all the operations on the output of the synthetic data generator, so essentially the synthetic data, remains private. And no matter what you do with that, you're not bounded by sort of exhausting the privacy budget due to the composition, right? You're performing your analysis and operations on already differentially private data, which is what I have just said, right? And in addition to that, your attack surface, if you don't share the model that generated the data, is a little bit more slippery. So for realistic attacks, again, you have more details that can be obscured if you just provide a view of the data and not the model that generated the data. So you don't have access to the model weights, for example, right? We can use the differentially private SGD to train a generative model on data, and the way it looks like, we fine-tune a language model on private data with DPSGD. So this way our generator is differentially private, and we give us an input, the class label. So essentially, let's say we want to generate movie reviews, we say generate a positive movie review, and then as a target we say, and this is sort of the text that you need to generate. So we train a model on this kind of objective, and then when we have finished training the model, we generate our synthetic data. Again, the model is differentially private, so whatever comes out of the model is also differentially private. And we just prompt it with the labels that we want to generate the data for, let's say positive, negative, neutral movie reviews. And then we let it just generate the text. Then we take the text and we share that instead of the model or instead of some kind of privatized version of the original data set, right? So the way it looks like is, and this is a bit small, I realize, is like this. You have, you're the data owner. You have some kind of private customer data. You train a language model with differential privacy on that data using the labels or some kind of meta information as the prompts to generate then the full text. And then you throw away the differential privacy generator, and you only, first you generate the synthetic texts from this differentially privately trained model, again using the labels or some meta information as the prompts to generate the text. Then you throw away the differentially private model, and you only share the synthetically generated data. Now there's another approach which does it differently. That's using a genetic algorithm. It's very fancy. I think we don't have the time to look at that. Let's just skip that. You can look at it at the slides later. The question is how we then evaluate the generated data. And one approach is to, again, look at the utility, right? So we need to make sure that some kind of structure and relationships or similar results are similar based on the original data that you don't want to share and the synthetic data that you have generated. And usually this is done by training downstream models on the generated data. So if you generate data for sentiment analysis, then you train a sentiment analysis classifier and you compare the performance. And again, these evaluations are typically done at different privacy bounds to show that sort of the more privacy you add, the worse the performance generally becomes, and in relation to a non-private upper bound. And if you're generating data that doesn't have any downstream task per se, for text, of course, we always have the language model modeling as a downstream task, the next token prediction. And there are three sort of ways of evaluating synthetic data with this kind of downstream model training. One is you train on real data and test on real data. This gives you the upper bound. So how good you can get with all the other approaches, right? Then you have trained synthetic data and test on the real data. This tells you how well synthetic data can actually support downstream task analysis on real data. So let's say you want to share something about your internal task. So you share synthetic versions of that task to let people develop the best model. Then you take that model, apply it directly to your data. If you don't want to do that, you can also do the train synthetic, test synthetic. Here you don't really care about the performance per se, you just care about the ranking of a different sort of selection of models, whether it's preserved between synthetic data and the original data, which the use case here being, okay, you have some task, you give the synthetic version of that task to everyone here. They develop their own algorithm. They give you back the code. You look at on the synthetic data, you look at the best performing model, and you would hope that when you train it then on the real data and evaluate on the real data, it would still be the best model, the best architecture, right? So this looks somewhat like this, right? You have here at different epsilon levels, different privacies. You have different downstream classification tasks. you have different models or different approaches that can generate the data. And then, so the more you go towards the right, the lower the score generally becomes, because the utility degrades as your privacy budget becomes sort of tighter, right? The less privacy breach you want to incur, right? Something different is the fidelity, and that is sort of how the data looks in itself without any downstream task in mind. And of course, if you want to generally evaluate, let's say, two strings, whether they're similar to each other, you can do things like blue and rouge. But we can't do that. We can't go and do a comparison between reference and ground truth, because of course, the whole point of differential privacy is to break exactly this link. So instead, we need to evaluate somehow at the whole data set level. So we need to look at distributional differences. So for tabular data, it's simple, right? We can look at what is the distribution of this column versus what is the distribution of this column in the synthetic data. If they somehow match, for example, measured by KL divergence or MMD, right, then it's good. If they are very different, then it's not so good. We can do counts of sort of categories, right? We can do histograms of categorical values as well, and so on. Now for text, it's a bit harder because there are no obvious features of what we want to sort of compare on a corpus level. One is we can, well, if it's hard, we do the simple thing instead. We can look at simple heuristics. For example, we can look at the distribution of text lengths, or we can use some domain-specific metrics, or we can look at semantic similarity. So there's a metric called MOF, which compares sort of the generated corpus of text to the original corpus of texts. So here, this would be the sort of histogram comparison of the text lengths, right? So here between different examples, again, we just take all the lengths of the generated and the original texts. We bin them, we calculate the histograms, and we can do something like KL divergence in order to see how similar or how different they are. It's also very good to visualize. But let's look maybe at MOF. So this is also not specifically a privacy sort of specific metric. MOF calculates the semantic similarity of two different corpora. And the way it works is that we embed both the sort of the original reference and the synthetic text using a language model. We then jointly cluster these embeddings. And then like the original text is a bit more fancy, but what we actually do is we're computing the KL divergence between the cluster assignment histograms. So if we have each of the texts belong to some cluster, and then we calculate essentially the KL divergence between the original data points cluster assignments and the synthetic data points cluster assignments. And this gives us then a KL divergence score. We can map it back to a single score between 0 and 1, where 1 is essentially the same, or 0 is essentially completely different. So intuitively, again, we get two distributions that we need to match. If we have clusters that are more synthetic points than original points, these are so-called false positives. So these are regions in the sort of in the data space where are overrepresented by synthetic data. So there's no real original data that is sort of being clustered in this space. So these synthetic data points are kind of false positives. They don't actually represent any real data. Whereas on the other hand, if we have false negatives, so clusters where there's more real data points than the synthetic data points, then we have, these are the regions in the space where the examples are there, but they have not been generated by the generator, so they're not well represented in the synthetic data. Now, finally, we also want to evaluate privacy because, again, we need to make sure that our implementation is sound. We need to make sure there's no violations. And we, again, mount membership inference attacks against the synthetic data sets. In this case, we assume access to the data set. So this is, again, more on the theoretical side. And the way it works is we insert a canary, so a specific string into the private data set, and then generate data set with and without that canary. So this then forms our membership inference attack evaluation set. And then we measure the language modeling probability of the string with an n-gram language model optimized on the synthetic dataset. So here again, we go back to the very beginning of the day, to the n-gram language models. And the intuition here is that if S, the canary S was in the private data, then the synthetic dataset generated from this data should reflect S better, and thus assigning higher probability P of S for the language model optimized on the synthetic data. And we can use the probability of P of S to threshold over it and to draw the area under the curves, right? And here is sort of one example of those. And the takeaways here is that the membership inference attack performance mainly depends on the canary length. right, on the perplexity, so how unusual this canary is, and how many times it appears in the data also. So still it is much lower than attacking the model directly. So here we see this is the AUC curve for the attack against the model, and these are all attacks against the data. And this again shows that in real sort of setup, sharing synthetic data rather than sharing the model generated synthetic data gives a less sort of tangible attack surface. So the real world attacks, at least at this point, are much less successful against synthetic data than against the models. So now we've heard about LLMs a lot, and of course, for this topic as well, for synthetic data generation, LLMs are sort of handmade for this task, right? And there's a lot of approaches using LLMs to generate differentially private synthetic data, and they're typically evaluated on popular and public data sets such as tweets or movie reviews, right? Now, the chances are that LLMs that have been trained on all of the internet already have possibly encountered these data sets during training, and then this is sort of access to the data that has not been accounted for privacy, right? And the other point is that actual private data sets, let's say you have like a hospital data set or your organizational data set, it's not like tweets, it's not like movie reviews, it's probably somewhere, it looks very, very different. So it's very different from the general domain popular data that is being used to evaluate this data generation approaches. Now what we have done is we have used, created a benchmark to use sort of semi-private restricted data, which is unlikely to have been observed by public language models. We have correlated the performance, both the sort of the utility and the fidelity with the pre-training corpus leakage. So we can estimate how much of the data set that we're evaluating on has been seen during pre-training. And we have also conducted an extension essentially of the previously presented text-based MIA attack to perform an audit to identify potential privacy violations. And so these are the data sets. We can see some of them are free, but others have specific credentialed access, which you can't use to train LLM models on, at least in theory. And you can see that the performance sort of, or the quality of the data pretty much log linearly scales. So here, as measured by the MOF score, log linearly scales with how much of the data has been seen during pre-training. So the more data we see during pre-training, here citar are I think tweets, the better performance we get when we then evaluate these approaches. So more than anything else, these benchmarks evaluate how much the model can remember what it has seen during pre-training rather than how well it can generate synthetic and private synthetic data, right? And we have also found some privacy violations where, again, because of the fact that these tweets or these data points have been seen during pre-training, we actually get membership inference attack scores that are higher than the guaranteed bound of differential privacy, especially in the sort of low privacy regimes. Right, one final example is a favorite of mine. So we usually assume when we do that the label distribution that we condition the generation on is public, but it's not really public, or it shouldn't be, because, for example, in the Mimic3 dataset that we looked at in the beginning, 66% of the dataset are already identified by a handful of labels from the 50 most common conditions. And it's because these labels are very, very, very detailed. So if you look at the labels here, ICD-10 codes, such as bitten by turtle and shocked due to being struck by lightning. So there's probably exactly one person in the world that would have both of these labels, right? So you don't privatize these because you assume they're public, but this already uniquely identifies someone who had the unfortunate luck to be bitten by turtle and struck by lightning at the same time. So, and the other question is, of course, also, okay, if we don't use labels, how can we then, or using labels we can generate sort of classification data, but how do we deal with data sets like Vijay talked about before, relational data sets? How can we preserve the linkages between data tables or data points which are sort of sitting in different tables? One of the things that we have done is, again, I'm not going to go through the details here, but the general idea is to use privatized content, so the terms of text rather than the labels, in order to not make the generation conditioned on the labels, but rather on the text itself. And then, of course, we need to privatize those as well. And the way it works is by just fine-tuning a large language model, using essentially instruction tuning and formulating it correctly and using DP-SGD. There are some domain-specific evaluations that we use. So, for example, for clinical use cases, we might want to look at whether certain things or certain diseases co-occur to the same prevalence in the synthetic data as they co-occur in the original data, right? Like things like hypertension and diabetes. So there's a certain percentage of patients that have both. So we would want to preserve these relationships in the synthetic data as well. And again, we can get this counts and we can calculate the KL divergence, which would look somewhat like this. Again, for me, this looks slightly different. There's a gray invisible spike for OCP, but it doesn't look very well, right? And then when we look at sort of the examples as this approach outputs, so I've been trying to sell you this as the sort of the best thing since sliced bread. In reality, of course, there's still research to be done in order to make this more realistic. So even if you don't look at the text, if you just look at how the text is formatted, here you see in the middle is the source node, and on the left-hand side we have the LLM-generated example without differential privacy. So that sort of starts looking similarly, whereas on the right-hand side we have a private version of that. It does generate text. There is some sort of overlap of the terms that are being used, but just by sort of squinting your eyes and looking at it, you see that this text already looks structure-wise even very much different than this. But if we zoom into the text itself and then we go to doctors and ask, hey doctor, what do you think? Does this make sense? They say, yeah, I can't see anything that's wrong with it. Or maybe they say, well, there's something that wouldn't co-occur like that in a real example, right? So to wrap up, and this is the final slide with the ugly blue, which is not as ugly here. The key takeaways here that we have shown is depending on sort of on your stance towards privacy, right? Sometimes you need privacy, and then even if it's just mandated by law or to keep your competitive advantage. And de-identification here is not enough because we have shown examples that are vulnerable to inference. Membership inference is sort of the fundamental threat, and the differential privacy builds a quantifiable guarantee around that threat and is robust against any attacks that aim to perform membership inference. And this enables to train machine learning models privately, which then can be used to generate synthetic data that enables private data sharing to a certain degree. We have looked at how to evaluate the quality of both models and the data generated by these models, and we have mentioned the DP audits that help uncover bugs and implement sort of bugs and implementations and verify that your proofs are actually the sort of the worst case guarantee that your proofs guarantee is actually holding both in theory and in your implementation. Okay, thank you very much. I think we can do 1 or 2 questions, or we go and drink coffee. All right, the coffee it is.
Thank you, Dr. Schlegel. Now I would like to call Ms. Sriti Sarma to hand over the open applause.